Welcome to the deep dive.
So today we're really getting into something critical using machine learning
Right.
to predict, heart disease risk. We want to explore how these different computer models are actually analyzing medical data.
To flag things,
They
basically.
flag potential issues, right? Hopefully much earlier on.
Yeah, and this is so vital. I mean, as we know, heart disease is still a huge killer globally.
Absolutely.
And getting that early warning, identifying risks sooner rather than later, it just makes lifestyle changes, medical help, all of that potentially much more effective.
Totally agree. And for this deep dive, we've got this really interesting article. It details a project where they actually compared different machine learning models.
Yeah, kind of a head-to-head.
Yeah, seeing which one was best at classifying heart disease. And they used that well-known UCI heart disease data set.
Right, the UCI data. So
Yeah.
our mission today really is to figure out which of these approaches actually came out on top, for predicting heart disease with this data.
And we want to dig into why. What factors were important? How well did they actually perform?
Sounds good. Okay, so let's start with the foundation, the data itself. The article focuses on this UCI heart disease data set. You said it's well known.
Yeah, pretty standard in this kind of research. It has medical info from just over 300 individuals.
Okay.
And for each person, there are 14 variables. So 13 attributes, things they measured, plus the one target variable, does the person have heart disease or not?
14 data points per person. So what kinds of things are we talking about?
Well, you've got the basics like age and sex, but then it gets into very specific cardiac stuff, like the type of chest pain someone reported, was it typical angina, non-anginal pain, etc.
Okay, so quite detailed on the symptoms. What else?
Then there's resting blood pressure, that's TRES-BPS in the data measured in mmHg, serum cholesterol, col in mgdl.
Right.
Also, fasting blood sugar specifically, whether it was over 120 milligl, that's FBS.
Okay, got it. And ECG results.
Yep. Resting electrocardiographic results, RESTEG. So whether it looked normal or had certain abnormalities like STT wave issues or signs of left ventricular hypertrophy,
Wow, okay.
and it doesn't stop there. Maximum heart rate achieved during exercise thaw-lash. Whether exercise actually caused angina, that chest pain, exang,
Right.
and old peak, which is the amount of ST depression seen on the ECG during exercise compared to when resting.
It seems really specific.
It is. There's also slope, the slope of that peak exercise ST segment, and Kayla, the number of major blood vessels highlighted during fluoroscopy.
Fluoroscopy, that's like an X-ray movie to see blockages.
Essentially, yeah. And finally, Sela, the results from a thallium stress test, which looks at blood flow, and then the big one, the target. 0 for no heart disease, 1 for yes, heart disease present.
So a really rich data set. Where did it all come from?
It's actually a mix from 4 places: Cleveland, Hungary, Switzerland, and Long Beach V, and it dates back to 1988.
Interesting. So older data, but from multiple sources. Okay, so you have this raw data. It probably needs some work before you can feed it to a model, right?
Right.
The article mentions pre-processing.
Oh, absolutely crucial. You can't just throw raw data at these models usually. You need to tidy it up.
Tidy up how?
Well, dealing with any missing values, maybe some tests weren't done or data wasn't recorded, removing duplicate entries, which could bias things,
Okay.
making sure the data types are right, like numbers treated as numbers, categories as categories, and importantly, addressing outliers.
Outliers, like extreme values.
Exactly. Someone with, say, wildly high blood pressure compared to everyone else. Sometimes these can skew the results, so you need a strategy to handle them.
Makes sense. Clean the data first. Then what? Did they just start building models?
Not quite. The next step is usually exploratory data analysis, or EEG, basically getting a feel for the data.
Looking for patterns.
Yeah, understanding the distributions, the basic statistics. The article shares some of that. Like, the average age in the data set was about 54, with a range from 29 up to 77. Average resting blood pressure was around 130, cholesterol about 242, average max heart rate near 150.
Gives you a baseline picture of the group.
Exactly. And that ST depression measure, old peak, averaged just under 1. Another key point from EDIA was the target variable itself.
The presence or absence of heart disease.
Right. It was relatively balanced. Around 56% had heart disease and just under 45% didn't.
And why is that balance good?
Well, if you had, say, 95% without heart disease and only 5% with, it's harder for the model to learn the patterns of the smaller group. A more balanced data set usually helps build a better classifier.
Got it. Okay, so after looking at the basics, did they look at how things related to each other? Like correlations?
Yes, that's a huge part of EDA. looking at how these different factors correlate with the target having heart disease. And the article highlights some strong ones.
Such as?
Strong negative correlations were found with caught the number of major vessels seen.
Okay, negative correlation. Remind me what that means practically. Fewer vessels seen, higher risk.
Precisely. In this data, fewer vessels visualized correlated with a higher likelihood of the heart disease diagnosis. Same strong negative link for old peak, ST depression, and exang, exercise angina.
So less ST depression and no exercise angina were linked to higher risk here. That seems a bit counterintuitive.
It can seem that way without the full clinical context, but that's what the correlation in this data set showed. Also, the thallium scan result, and interestingly, sex, being female, had strong negative correlations with the target.
So being female in this data set was linked to a higher likelihood of diagnosis.
According to the correlations found in this specific 1988 data set, yes. It's important not to overgeneralize, but to report what the data showed.
Okay, what about positive correlations? Things where higher values meant higher risk.
Yeah, there were strong positive ones too. Slope, that ST segment slope we mentioned, had a strong positive correlation. Same for CP, chest pain type, and thalash, maximum heart rate achieved.
So a steeper slope, certain chest pain types, and a higher max heart rate were associated with more risk in this study.
Correct. Then there were weaker links too. Age, resting blood pressure, cholesterol showed weaker negative correlations with the target.
Weaker negative, so slightly higher age, BP, cholesterol meant slightly low risk. Again, a bit surprising.
It highlights why correlation isn't causation and why context matters. These are just statistical relationships in this particular data set. Fasting blood sugar, FDS, and resting ECG, RESTEG, had weak positive correlations.
Okay, so based on all these correlations, did they narrow down the features they used for the actual models?
Yes, exactly. They focused on the one showing stronger relationships. The article lists 9 key features selected: CP, thalash, slope, old peak exang, Cathal, sex, and age.
Right, the heavy hitters based on the EDA. So 9 features selected. What next? Do they just feed these into the models?
Almost. 2 more important prep steps mentioned: scaling the data and using principal component analysis, or PCA.
Scaling. Why is that needed?
Well, look at the ranges. Age might go from 29 to 77, while ST depression old peak goes from 0 to maybe 6.2 if you don't scale them.
The bigger numbers dominate.
Exactly. Features with larger numerical values could unfairly influence the model just because of their scale. Scaling puts everything on a comparable level, maybe between 0 and 1, or with a mean of 0 and standard deviation of 1.
Okay, levels the playing field. And PCA, principal component analysis. Sounds complex.
It's a technique for feature extraction or dimensionality reduction. It tries to find the underlying patterns in those 9 features and create new features, principal components that capture most of the original information but are uncorrelated with each other.
So simplifying the input while keeping the essence.
That's a good way to think about it. You often use something called a scree plot to decide how many of these new components to keep enough to explain most of the variance in the data without keeping too much noise.
And how many did they use here?
In this case, they ended up using 9 principal components, so they transformed the original 9 selected features into 9 new ones via PCA.
Okay, data cleaned, explored, key features selected, scaled, and even transformed to PCA. Now it's time for the models.
Now it's time. The article mentions they trained 4 main types of machine learning models.
Which ones?
Logistic regression, a classic statistical model often used for classification. Then decision tree, which makes predictions based on a series of if-then rules.
Like a flowchart.
Sort of, yeah. Then random forest, which is actually an ensemble of many decision trees working together, usually more robust.
Okay.
And finally, a neural network, specifically a multi-layer perceptron or MLP, inspired by how the brain works, with layers of interconnected nodes.
4 different approaches. How did they test them?
Standard practice? They split the prep data. 80% was used for training the models, letting them learn the patterns. The remaining 20% was held back as a testing set.
See how well they performed on data they hadn't seen before.
Exactly. It gives a more realistic measure of how the model might perform in the real world.
So what were the initial results, just after training on that 80%?
The article gives some initial figures. The decision tree scored lowest on accuracy, around 75%. Its recall was 76%.
Recall. Let's define that again.
Recall, or sensitivity, is crucial here. It measures how many of the people who actually had heart disease were correctly identified by the model. High recall means fewer false negatives.
Right. Missing someone who has the disease, a false negative, is obviously bad in this context.
Extremely. So decision tree. 75% accuracy, 76% recall. Random forest did better initially. 81% accuracy and a higher recall of 85%.
Okay. What about logistic regression and the neural network?
The initial numbers aren't explicitly stated right there, but looking ahead at the post-tuning results, it seems they were also probably around the 81% accuracy mark initially, similar to random forest.
So random forest had the best initial recall, but they didn't stop there, did they? You mentioned tuning, hyperparameter tuning.
Correct. The initial training uses default settings for the models. Hyperparameter tuning is like fine-tuning the engine. You adjust the model's internal settings, not the patterns learned from data, but the parameters governing the learning process.
To squeeze out better performance.
That's the goal. Finding the optimal configuration for each specific model on this specific data.
And how do you find that best configuration? Guesswork.
Not quite. They used a technique called grid search. You define a grid of possible settings for the important hyperparameters.
Like what kind of settings?
For logistic regression, it might be things like the maximum number of iterations, maxiter, or the type of solver used. For decision trees and random forests, it could be the maximum depth of the trees, the minimum samples needed to split a node.
Okay.
For the neural network, it'd be things like the number of hidden layers, the number of neurons in each layer, the activation functions, the learning rate. Lots of knobs to turn.
So grid search tries all the combinations.
Pretty much. It systematically goes through all the combinations you defined in the grid and evaluates the model for each one, usually using cross-validation, to find the combination that gives the best performance metric, like accuracy or recall.
Sounds computationally intensive.
It can be, definitely, but it's thorough.
So did this tuning make a difference? What were the results after grid search?
Yes, it definitely impacted some models more than others. Logistic regression didn't see much change. Its accuracy stayed around 81%.
Okay.
But the decision tree, big improvement. It jumped from 75% accuracy up to 82%.
Wow, tuning really helped that one.
It did. Random forest saw a slight bump from 81% up to 82% accuracy.
Okay, matching the tuned decision tree.
And the neural network, MLP, showed the biggest gain overall, going from around 81% accuracy up to 84% after tuning.
So after tuning, the neural network actually had the highest accuracy score, 84%.
Hey, based purely on that accuracy metric reported after tuning, yes, the MLP hit 84%.
But accuracy isn't the whole story, especially here. The article then talks about ROC analysis.
Right. ROC stands for Receiver Operating Characteristic Curve. It's another way to evaluate classifiers, especially when the balance between detecting true positives and avoiding false positives is important.
How does it work?
It plots the true positive rate, which is the same as recall or sensitivity, against the false positive rate, how often it incorrectly flags someone without the disease, at various different decision thresholds for the model.
Thresholds.
Yeah, most models output a probability, say from 0 to 1. The threshold is the cutoff point, like below 5, where you decide above this probability means disease, below means no disease. The ROC curve shows performance across all possible thresholds.
Okay, and what's the key number from that? AUC.
Exactly. AUC stands for area under the curve. It summarizes the entire ROC curve into a single value between 0 and 1.
What does the AUC value tell you?
An AUC of 1 is a perfect classifier. An AUC of 0.5 is basically random guessing. So the closer to 1, the better the model is at distinguishing between the positive cases, heart disease, and the negative cases, no heart disease.
And who won on AUC?
According to the article, Random Forest had the highest AUC score at 91%, or 0.91.
Ah, interesting. So even though the neural network had slightly higher accuracy after tuning?
Random Forest was better overall at discriminating between the classes, according to the AUC metric. Logistic regression was apparently a close second in AUC.
So an AUC of 0.91 for random forest.
Yeah.
That means it's pretty good at telling the difference.
Yeah, roughly speaking, it means if you randomly pick one person with heart disease and one person without, there's a 91% chance the model will assign a higher risk score to the person who actually has the disease.
Okay, that makes sense. And you mentioned the trade-off on the ROC curve between true positives and false positives.
Right. Choosing a specific operating point on the curve, which means choosing a threshold, involves a trade-off. If you lower the threshold to catch more true positives, increase sensitivity to call.
You might also get more false positives, more false alarms.
Exactly. You increase the true positive rate, but the false positive rate might go up too if you raise the threshold to reduce false alarms.
You might miss some real cases. Lower recall.
Correct. So the choice of threshold depends on the application. In heart disease screening, you might tolerate slightly more false positives to ensure you catch as many true cases as possible.
So, weighing everything accuracy after tuning, recall, AUC, which model did the study conclude was the best overall?
The conclusion pointed to Random Forest as the best performer overall. It achieved high accuracy, 82% after tuning, and had that top AUC score of 91%.
Was there any caveat?
Just a note that the optimal threshold found for Random Forest during tuning was relatively high, which, as we just discussed, could potentially lead to more false positives compared to a lower threshold, even though its overall discrimination, AUC, was excellent.
Okay, so Random Forest wins with that small note about the threshold. The project didn't just stop there, though. They talked about deployment.
Yeah, putting it into practice, potentially. They took the best model, the tuned Random Forest, and saved it. The article mentions using a pickle file.
Pickle.
Yeah, it's just a common way in Python programming to save a trained machine learning model so you can load it up later without retraining.
Okay, so they saved the model. Then what?
They built a dashboard using a tool called Streamlit. This created a simple web application.
What does the app do?
It allows a user to input their own values for those key medical features, age, sex, cholesterol, etc. And the app uses the saved Random Forest model to generate a prediction about their heart disease risk.
Wow, so a practical tool based on the research.
Exactly. And they even shared links to the live web app and the project's code on GitHub, making it quite transparent.
That's really cool.
Yeah.
Okay, so wrapping up this deep dive, the main takeaway seems to be that machine learning, particularly Random Forest in this case, especially after careful tuning,
Shows real promise. It can effectively predict heart disease risk by analyzing these various medical indicators.
yeah, a powerful tool for potentially catching things early.
Definitely. But as the study implies, and as we discussed, it's absolutely vital to think about that trade-off. Sensitivity versus specificity. How many false alarms are acceptable to catch more true cases? That needs careful thought for real-world use.
Which really leads us to a final thought, doesn't it? As these predictive models get more sophisticated, more integrated into actual healthcare, how might that fundamentally change things, like preventative medicine, or even just how you or I manage our own health?
It's a huge question. Could we see truly personalized prevention plans based on these kinds of risk scores? How does the doctor-patient relationship change?
And what about the ethics, data privacy, potential biases in the algorithms? Finding that balance between leveraging this amazing technology and keeping the human element central to care.
Exactly. It's not just about the tech. It's about how we use it wisely and ethically. Definitely something to keep thinking about.
Absolutely. Well, this has been fascinating. Thanks for joining us on The Deep Dive.